good to remind yourself that everything we're seeing today is actually right at the edge of experimentation. I mean, answer soon is something we've actually heard before today. That's what makes this so cool. I'm curious about the invention of these things, like LIGO, for instance. Was that an individual that came up with that idea?
The idea came up in the 1970s. Basically 2 or 3 individuals putting all the different pieces together and convincing themselves that you could actually reach this mind-boggling precision. Yeah. And so the idea goes back to the 70s, and then it took some 20 to 30 years to actually put the paper in the back of the envelope calculations that were done during one night in a hotel room into reality, and actually putting all the little details in that were needed along the way to make it work.
Of course, identifying the interferometry as an amazing tool to do precision measurements of displacement. This goes back to the late 1800s, where people used it to show that the ether concept was a no-go. And then as time kept going, well, people improved it even further, and then it was Ray Weiss and other people independently realized, okay, you can take it to the realm of measuring using for gravitational wave measurement. But it still required like 4 more decades of improvements and additional technology that had to be conceived and then implemented to get to where we are today.
And balloons?
Well, I think the first hot air balloons were in the 18th century.
Yeah, the Montgolfier.
Yeah, those guys. But they were just launching cows or something.
Ducks.
Ducks, I'm sorry, yes. Cows would be a bit of a challenge. Balloons for scientific purposes, certainly in the 19th and 20th centuries, people were doing that. As soon as you could start actually having the automation, such as you could fly one without people in them, people started doing that. So it's been certainly an obvious thing to try for as long as people have had balloons. So there's some groundbreaking work done in the 60s by an experiment called Stratoscope 2, Stratoscope 1. These were some of the first automated unmanned experiments trying to get out of the atmosphere to do astrophysics. But it's been sort of this ongoing process. And of course, every time you fly, it's like, oh, I invented something new. And then you read about it, it's like, well, no.
Yeah, well, that's that feedback between results and ideas.
Oh, absolutely.
Question, anybody has a question? Okay, right there.
Yes, thank you. Are you able to give us some idea what this fabric consists of? What are these waves being propagated through?
That's a very interesting question. So first, let me just go a step back. I mean, as in physics or in science as a whole, we always have models for nature. And so whether it is a fabric or not, it's a separate question. Picturing as a fabric governed by a set of equations, and this fabric behaves in many ways like the standard fabric that we would just come and choose and play around with, makes total sense. We make measurements, we predict new things, we go and contrast with observations, and as long as that stays consistent with observation, it's a working model. But that need not be true, right? I mean, and this is always true in science regardless. So we have, this amazing thing that we can use math to comprehend the universe is perhaps the most incomprehensible thing we have at our disposal. But the fact that it makes sense, well, just it's something that works. We keep going forward, and one day it might show cracks, and then we'll decide that we need a different model. But aside from that, anything that you can picture as a fabric do, the space-time seems to have no problem doing it.
The way I like to think about it is that those lines in Harold's pictures are all supposed to be straight lines. And so the fabric is like space itself. It's saying space itself behaves as if it were a fabric. It's not that it is a fabric. So straight lines converge. Like, what does that mean? How can parallel straight lines converge? Well, because space itself is bent. It's like drawing straight lines on the surface of the Earth. If you take 2 straight lines from the equator and send them straight north, they'll converge at the North Pole. It's like, well, that line was straight. What do you mean it bent? But it's like that. So it's not, the fabric isn't made of anything. It's space itself, which is curved.
If you're measuring gravitational waves from the beginning of the universe, how do you know that? How do you know that it's coming from the beginning of the universe as opposed to some 2 black holes merging somewhere else.
Yeah, that's great. It's because of the angular size of them, right? So two black holes are going to be on the sky, there, or there. And what we're seeing with these ones is they're extremely large in scale. Could be several degrees up to tens of degrees across. And so the region that's emitting them is very large spatially. So that's how we tell that it's something that's extended, and it's coming from when the universe was much denser and much smaller, and those points were much, much closer together. If that makes any sense.
And also Bart's gravitational waves, those from the beginning of the universe, we are not seeing the gravitational waves themselves, but we are seeing the effects those waves have on the gas in the universe 100,000 years after the Big Bang.
And also between here and there. Yeah. It's distortions in space altogether.
So that means these waves have already had to be there 100,000 years after the Big Bang, whereas the black holes I was talking about, those are actually really, really young. Those were only about a tenth of the age of the universe.
Do you have an anticipation of what you would see once you start to gather data from the very early?
Absolutely. The theorists have provided us with a very clean signal we're looking for. Not in terms of what it looks like on the sky, but in terms of the distribution of sizes of these things. It'll look kind of like noise, but it will have a particular angular power spectrum. The power on things that are this big will be this, and smaller will get bigger, and smaller will be bigger still, and it starts getting smaller again as you get to different angular sizes. So kind of the statistical distribution of these things is well described. The particular instance of them is not. I don't know if that helps at all.
Well, it does tell me you've got an idea.
Yeah, I can try, like you can look at two pictures of just, you can imagine two pictures that look just like noise, but in one case, all the little noise dots are really small. In another case, it's kind of wavy, right? And that would be like different angular distributions. And they tell us exactly what that's supposed to be. It's supposed to have this scale of waves on the sky. Too small? Oh, it's not that. Too big? Oh, that's weird. It's not that. It's something in between. And they have a very precise description of what that's supposed to look like, and so we can compare against theory.
I know I have to say that black holes don't suck, but why then would two of them coalesce into one bigger one?
So if we look at, say, us and the sun, so we're going around the sun, and if you think of it in Newtonian terms, we should be going around it forever and nothing happens. But now if you add the departures from it that are predicted by general relativity, angular momentum is slowly lost. Because of that, then the orbit becomes tighter. And this is a runaway effect. So if they are close enough, they will merge in less than the age of the universe, and then there is no escape. A black hole, a single black hole, which will be the end product of two black holes coming together, is an unavoidable fate for the system. Based on general relativity. Similarly, any binary will do that. I mean, it could be that the binary will take much longer than the age of the universe, in which case they wouldn't merge. And this is why we concentrate on binary neutron stars and binary black holes and black hole neutron stars, because those are the systems that are generating the strongest gravitational waves. They are losing the angular momentum in the faster rate, which will allow them to merge in a reasonable amount of time.
And the way these two black holes or two neutron stars end up very close to each other to begin with is because they form from two stars that are already orbiting about each other. Most of the stars in the universe are actually not alone like our sun, but most of the stars actually come in pairs, like the two suns of Tatooine that already are orbiting about each other. And if at the end of the lives of these two stars, each one of these stars forms either a neutron star or black hole, then you have the two compact objects, the black holes or the neutron stars, already close to each other and orbiting about each other. And this is now where gravitational waves can take over and get them even closer together until they finally run into each other.
I wonder if you could comment a little bit more on the notion that when two black holes coalesce, that all of the energy is transmitted through gravitational waves. There's no other kind of energy that's emitted, such as electromagnetic radiation.
That's a very good question, and it goes back to the beginning of Bart's talk, where he showed the various objects that emit various frequencies of electromagnetic radiation. The important point is to make electromagnetic radiation, you need matter. You need gas, you need a hot filament in a light bulb, you need something. Black holes themselves are consisting only of vacuum. They're only curved space and warped time. And as long as you only have vacuum, even if the space and time is curved, there's nothing there that could make electromagnetic radiation. You need another star nearby. You need gas falling into the black hole, something else, in order to make electromagnetic radiation. And it turns out for the LIGO-sized LIGO-sized black holes, our understanding of how these objects behave in the universe indicates that there should be no gas nearby, and therefore nothing that can emit electromagnetic radiation. If we have a neutron star in the system, a black hole and a neutron star or two neutron stars colliding, then we have a lot of matter around, and so at that point there will also be not only gravitational waves, but also an electromagnetic firework accompanying it.
So yeah, let me add one thing. So we keep concentrating on LIGO because that's the detector we have. That's the window between a hertz and a kilohertz that has been opened by LIGO. But just as in the electromagnetic camp, where we have microwaves, the optical, the ultraviolet, the gamma ray, the X-ray, etc., the whole field is just moving forward to open several bands. We're going to hear later about using pulsars to try to see at a different chunk of the frequency window. Then there is a planned detector that will go in space called LISA. That will be thinking or trying to target black holes not of these types, not of these sizes, but of the million to tens of millions of solar masses like Daryl discussed this morning. Those, we believe, will typically have enough matter and gas around them because they are powering the active galactic nuclei, etc., that those will be examples where the binary black hole comes together, these supermassive binary black holes come together. We'll also have gas to then do something interesting on the gas, and then we're going to have a combined flash. But we're just at the beginning. So we are spoiled in some ways by looking at the development of the electromagnetic side of our search for interesting things in the universe. We have several hundreds of years there where each individual band has been opened and has been gone into precision. We're at the very early epochs. It's like the picture that we saw today of Kobe going to WMAP, going to Planck, where we went from a very fuzzy image to something very precise. So today we have the fuzzy image of a single window, but this is just starting. The whole future would be amazing on the gravitational wave camp with everything that is planned moving forward.
This is a bit of a Star Trek question. Most science fiction features a great lumbering spaceship hovering effortlessly a few hundred feet above the planet's surface. So my question is, what is gravity? Why is it there? And do you foresee the human race being able to control it?
Okay, so it's an excellent question. Gravity is an attractive force between any two objects in the universe. The apple is attracted to the Earth, and therefore it falls from the tree. The moon is attracted to the Earth, and therefore it goes around the Earth, and so forth. Or, if we switch over to the Einsteinian picture, gravity is represented as a curvature of space and time itself. Why it is there, I don't know. I can tell you how it behaves, but not why it is there. And currently, all indications is that gravity is always attractive and never repulsive. And as such, I am not aware of any mechanism scientists or engineers could come up with which you can actually float the spaceship nicely above the ground.
That is not to say the theories, we have sometimes plenty of time in our hands, and people have thought of very crazy ideas that could do that. That it will involve some type of matter that we have no evidence whatsoever that it exists. But if it is there, okay, there are models. No one is spending too much time on this, but we do what we can.
But then also, 200, 300 years ago, everybody was absolutely certain that humans could never fly.
That's not true.
Luis, you use the analogy of the ripples around a duck or whatever. Those ripples dissipate eventually. Do gravity waves stay the same size as they move through the universe?
So the wavelength stays, but as we heard this morning, if we have an expansion, so there is a redshift, so then they go to the red. And the intensity goes down as one as there are. So yes, I mean, the farther we are, so the example would be the very same that event that Harald showed. Had we been sitting about 1,000 kilometers away from the binary black hole mergers, we didn't need LIGO. We would have heard the collision because our skulls are much more rigid, our middle ears would have moved around, and that would have given our brains the right signal to detect the gravitational waves without having to spend a dime. Of course, we would have to be in this uncomfortable position of being too close to the black holes. But where we are, they have decayed enough that we needed about $1 billion worth of experiment to actually go and get them.
There's actually an interesting aspect to the question you asked about the ripples in the pond. The ripples, water waves in a pond move at different speeds with different wavelengths. The long wavelength water waves move faster. Therefore, if you throw a stone in the water, a certain distance away later on, you will first see the long wavelengths and then later on the shorter wavelengths. The gravitational waves, all of them, no matter what the wavelength, they move precisely with the same speed. They move with exactly the same speed to about at least 1 part in 10 to the 20th, and that's the speed of light. And so that's another prediction of Einstein, that gravitational waves should move with the same speed, no matter what the wavelength.
The speed of light?
The speed of light. And that's also one of the tests we could make with these very first gravitational wave detections already.
Yeah, I was just wondering, we know that gravity waves distort space by contracting and stretching. Is it possible gravity waves can also affect time that way?
Very much so. So that's one of the tenets of Einstein's theory of relativity, that space and time are not distinguishable. So we speak as space-time. Everything gets distorted.
If time distorts, that means some part of time goes more quickly when it's, let's say, contracted, and then when it's stretched, it goes more slowly.
Yep. By a 10 to the minus 21 amount.
Right.
There's actually much bigger effects on the rate of flow of time. The wave-like features come in at this really small magnitude, but there's also stationary effects that the deeper you are in a gravitational field, the more slowly time flows. Atomic clocks by now are accurate enough. If I had a clock here in front of me and another clock up where I used it, there's 1 or 2 meters of height difference. Those clocks would go at different rates, and this can be measured and is measured. People are actually talking about using extremely precise clocks in geodesy to measure height in places on the Earth where it's hard to get to.
I remember reading many years ago about the concept of pinhole-sized black holes, and I haven't heard much about it lately. I'm just wondering if there's been any development in our understanding of those.
So Daryl mentioned some of this morning. So the very, very tiny black holes, those we believe will be described by the process of Hawking radiation, and it will take very little time in basically disappearing. That's why we're looking for larger black holes. And some of these larger black holes, which in the right regime may possibly even be part of what we were hearing this morning about dark matter. But that's a question we want to try and see if we can answer by gravitational wave measurements. But the small black holes, those take too little time and then to cease to exist.
I have 2 questions about SPIDER. I'm wondering if it's feasible at all to reuse any of the equipment or to do a second version that could be reusable. And secondly, so many of these concepts about everything we talk about today is so abstract and so hard for people to understand. And I think that turns off the general public to a great extent. But SPIDER seems really interesting to me that it's quite comprehensible to most people, understand balloons and things like that. And the idea that, like, I'm wondering if you, for example, put a camera on it just to get pictures of, like, it's way up there. Look at what we can see. That has nothing to do with detecting gravitational waves, but would engage a lot of people. Is there anything like that you've done or thinking of doing?
See, the first question was how much of it is reusable? We got back the telescopes that were inside the cryostat, so we're flying those again. We got back most of the control electronics, and it seems to be okay. The gondola frame and the motors were all destroyed, so we're replacing those. And we are flying again in about 18 months. The second question is, have we happened to have accidentally flown GoPros on our payloads and uploaded images of sunrises and the ground and things on YouTube? That would be yes. So, yeah. So you can either look up. I'm not sure what the right search phrases are for YouTube, but there's a number of videos. We had one from BIT a couple years ago where we actually saw the sunrise from the balloon altitude, which is gorgeous. Going from the dark sky to the sun coming up, and you see the curvature of the Earth. So yes, we have some of these videos. It's pretty fun.
But no sunsets.
No, we can play it backwards. I'm sure that's fair, yeah?
Future launch of Spider, will that be to see more of the sky or to see the part of the sky you've seen in more detail, or what are the objectives for another go?
Okay, well, the biggest challenge for these gravitational wave measurements from balloons, these polarization measurements, is that our galaxy has dust in it. And this dust, the emission from the dust is also polarized. Now, it's warmer, and so it peaks at a shorter wavelength. So if you have multiple frequencies, multiple detectors, you can tell the dust from the cosmic microwave background, but we need to have the multiple colors. So our first flight, we flew 2 colors, and the next flight we'll fly 2 more, and with those 4, we'll be able to subtract out any semblance of dust left. We're temporarily, in our current analysis, using the dust measurements from Planck to some level remove the dust, but having Spider ends up being more sensitive on this part of the sky. Planck measured the whole sky. We're just focusing on a smaller part of the sky. The second flight, our dust measurements will be more precise, and we'll be able to do a better job at subtracting out the dust to make sure that we're really seeing what we think we're seeing and not seeing our own galaxy.
You were discussing the speed of time, or the rate of elapse of time, and considering that, what can be said about the characteristics of time itself in view of the behavior of the space-time matrix in relation to the black holes? Is time linear with the past, present, and future as we perceive it? Or is in fact time linear without a past, present, and future? Or is time actually non-linear altogether?
We believe and we hope that it's actually linear and always going forward. Near enough to black holes, actually inside event horizons, there are things called closed time-like curves, which are science speak for time machines. And the difficulty once you have time machines is that the whole notion of causality, that things that happen today determine how the future looks like, is breaking down. So if time machines actually exist, like they do inside black holes, then we simply wouldn't know how to deal with predicting the future anymore. And this is great in science fiction stories where you can go back into the past and kill the person who is going to kill your father. But in reality, it just causes so many troubles that we hope they don't have to go there.
Or we hope it does, but doubt it does.
Well, to the extent that we can use binary black holes to test these ideas, at least something we know or we think we can do is just assign an arrow of time based on thermodynamic arguments. And the fact that black holes that could merge do merge is precisely in line with that. So there is no inconsistency as to second law of thermodynamics still giving us the best arrow of time that we can think of.
To learn more about the early universe and the evolution of the universe, could you quickly just sort of give us a sense of how you think gravitational waves will open up more answers than we already have?
There are these models for what the very, very beginning of the universe was doing. There's a bunch of problems, curious things about the universe, like how uniform it is in very large scales, about the fact that parallel lines seem to stay parallel and don't do crazy things. A whole bunch of these problems with how the universe came to be And the only way that we have so far of probing those extremely early times is through these gravitational waves. Nothing else can travel through the universe at those incredibly high temperatures and densities. So at this point, it seems like it may be the only way of looking at that part of the history of the universe, which makes it kind of special.
So I could say, don't go around looking for trouble, but when there is one, I take a look because it might be interesting. And it could be that as we go along, I mean, there are some things, like we mentioned today, the cosmological constant. That's something that you added in, and it makes perfect sense. Observations are beautiful, and everything just points to it having to be there. But then there is a second school of thought that said, well, maybe that's the first sign that Einstein's theory of relativity has gone wrong. But that's one number so far. So we haven't had so far good ideas or good opportunities to test that. Now this is giving us some, right? We're getting gravitational waves. We're getting signals from the most extreme regimes of the gravity that we have access to with respect to gravity. Maybe something new will happen. And so that's what I'm looking forward. Till something odd happens, I'll just keep doing what I do, doing interesting things, trying to get the most out of the observations that we can from the physics we can control. But I'm most looking forward to surprises, something that we haven't thought of, and it's just hit us in the face and push us into new vistas. In here.
The speed of light, we've been told over and over, the speed of light is an absolute. Nothing can exceed the speed of light. It is there. We're stuck with it. Do we have any theory as to why it is an absolute?
So we have built very successful theories based on some symmetry principles. And one of them happens to be that. So Lorentz invariance postulates that. So it's a principle, it's a basic building block. And out of it, we have created the standard model that has passed with flying colors. Every single test we have put it through. And it seems to be doing the same thing on the general relativity front. That is, of course, not to say that this is an absolute truth in nature. It might show its cracks again. Again, it's one of these, looking forward to the day where it actually shows that crack, because it will significantly alter how we do things. Till that happens, we're going to first keep marching with what we have, trying to extract the most physics, and at the same time entertaining these ideas. And there are people actively doing this, where they actually violate Lorentz invariance, both in the description of general relativity or trying to make a connection with what we think at some point should replace general relativity and try to marry it with quantum gravity. And some of those at the basic ground level, you actually are violating such principle. What is true or not at the moment is a figment of theoreticians. And hopefully one day, as Matt was saying, nature will prove us right or wrong.
I think it's fair to say that the constantness of the speed of light can be thought of as an experimental result, first and foremost. And then there's theoretical reasons, the implications of that. It comes, like you said, it comes out of Lorentz invariance, but you want to measure whether or not that's true. So it sort of traces back to being an experimental truth, if that's helpful.
And that's actually precisely where it came from.
Yeah.
The speed of light was first measured to be constant. And only later came the theoretical underpinning. If space and time is actually combined into one space-time continuum, then you must have one characteristic constant speed, which happens to be the speed of light. The measurement came first in that regard.
In other words, it fits the theory, and that's why we have it.
No.
It fits the observation.
The theory fits the observation.
Yeah.
The observation comes first. Look, the speed of light is constant. Amazing. That's crazy. How can that be? Then you come up with a theory that's consistent with observation, and then it predicts more things, and you go and measure those, and you say, wow, this whole holds together. So, but the way I like to think about science is we're describing the behavior of the universe. So theories are a description of how the universe behaves. And so we go and we do measurements, we work on the descriptions, they work together. The theories maybe predict, oh, you should see this. If this is true, you should see that. We go and look for it. And then in the meantime, I say something else that we hadn't predicted. It's like, well, but in the end, it's an effort between experiment and theory to make a description of the behavior of the universe. And one of the things that we've measured is that the speed of light is constant.
I'm not married to any single piece of physics that I know of. I mean, if it shows to be wrong, good, I move on.
Well, that's even true of the speed of light, because it seems to me like every decade there's a claim for some observation that could be explained by something violating the speed of light.
And so far, every time it's turned out that that was
Exactly.
wrong.
Yeah.
The speed of light was constant, there was some other problem.
But it's not like scientists are rejecting the possibility.
No, and as Harold said, one of the important measurements one of the important things they looked at right away from these LIGO things were the gravitational waves at all wavelengths traveling at the speed of light. And so far it appears that they are. This is something we're always looking at. We would love to see a violation of this. So far we haven't. So the way to think about it is not that a theoretical model is true, but that a theoretical model accurately describes measurement. That's the point. What we're always trying to do is come up with an experimental model that accurately describes what we measure. And when those things are merging together, we say, this is a good theory. When they disagree, it's a bad theory.
Great. Yeah, sorry.